Hello students, in this video we are going to discuss about microprogrammed control. The control signals required inside the processor can be generated using a control step counter and a decoder or encoder circuit. An alternate scheme called microprogrammed control, in which control signals are generated by a program similar to machine language programs. First, I will tell you what is a control word. A control word is a word whose individual bits represent the various control signals. Each of the control steps in the control sequence of an instruction defines a unique combination of ones and zeros in the control word. An example of the control word or the micro instruction is being shown in the diagram. A sequence of control words corresponds to the control sequence of a machine instruction consisting of micro routine for the instruction, and the individual control words in this micro routine are referred to as micro instructions. The micro routines for all instructions in the instruction set of a computer are stored in a special memory called control store. The control unit can generate the control signals for any instructions by sequentially reading the control words of the corresponding micro routine from the control store. This suggests organizing the control unit as shown in the figure. To read the control word sequentially from the control store, a microprogram counter is used. Every time a new instruction is loaded in the instruction register, the output of the block labeled starting address register is loaded into the microprogram counter. The microprogram counter is then automatically incremented by the clock, causing a successive micro instruction to be read from the control store. Hence, the control signals are delivered to various parts of the processor in the correct sequence. One important function of the control unit cannot be implemented by the simple organization shown in this figure. This is the situation that arises when the control unit is required to check the status of conditional codes or external input to choose between the alternate course of action. An alternate approach to use conditional branch micro instruction is being shown in the diagram. In addition to the branch address, the micro instructions specify which of the external input conditional codes or possible bits of the instruction register should be checked as a condition for branching to take place. The instruction branch may now be implemented by a micro routine such as shown in the figure. After loading this instruction into instruction register, a branch micro instruction transfer control to the corresponding micro routine, which is assumed to start at location 25 as shown here, right? This address is the output of the starting address generator block in the previous figure which I have shown. The micro instruction at location 25 tests the n bits of condition code. If this bit is equal to 0, a branch takes place to location 0 to fetch a new machine's instruction. Otherwise, the micro instruction is at location 26 is executed to put the branch target address into the register Z as in step 4. The micro instruction in location 27 loads this address into the program counter. To support microprogramming branching, the organization of the control unit should be modified as shown in the figure. The starting address generator block of the figure becomes the starting and branching address generator. This block loads a new address into the microprogram when a micro instruction is to do so. To allow implementation, a conditional branch input to this block consists of the external input and the conditional code as well as the content of the instruction register. In this control unit, the microprogram counter is incremented every time a new micro instruction is fetched from the microprogram memory, except in the following situation. When a new instruction is loaded into the instruction register, the microprogram counter is loaded with the starting address of the microroutine for the instruction. When a branch micro instruction is encountered and the branch condition is satisfied, the microprogram counter is loaded with the branch address. When an end micro instruction is encountered, the microprogram is loaded with the address of the first control word in the microroutine for the instruction fetch cycle. Let us now discuss about some drawbacks of microprogram control. Assigning individual bits to each control signal results in long micro instructions because the number of required signal is usually large. The next thing is available bit space is poorly used because only a few bits are set to 1 in any given micro instruction. The solution for it is the signals can be grouped because most signals are not needed simultaneously, and the other thing is many signals are mutually exclusive. So grouping the control signals into field requires a little more hardware because decoding circuit must be used to decode bit pattern of each individual field into individual control signals. So the main advantage is this method results in a smaller control store. That is, only 20 bits are needed to store the pattern for 42 signals. And having a separate microroutine for each machine instruction results in a large total number of micro instruction and a large control store. Also, the execution time is longer because it takes more time to carry out the required branches. These are all some of the drawbacks of the microprogrammed control. A simple approach is to allocate one bit for each control signal, which results in a longer micro instruction since the number of control signals is usually very large. Few bits are set to 1 in any micro instruction, resulting in a poor use of bit space. Reducing the length of the micro instruction by taking advantage of the fact that most signals are not needed simultaneously and many signals are mutually exclusive. For example, only one ALU function is active at a time. Source for a data transfer must be unique. It can't be of same for all the data. Read and write memory signal cannot be activated simultaneously. So grouping mutually exclusive signal is in the same group, and at most one micro operation can be specified per group. And using binary coding scheme to represent signals within a group would be a better idea. Let us have an example. If ALU has 16 operations, then 4 bits can be sufficient. Grouping register output signal into same group since only one of the signal will be active at any given time. Can you guess why? If the central processing unit has 4 general purpose registers, then PC out, MDR out, Z out, offset out, R out, R1 out, R2 out, R3 out and temporary out can be placed in a single group, and 4 bits will be needed to represent these things. Now let us discuss about the forms of organization. There are two forms of organization. One is nothing but of little coding or horizontal organization. Other is nothing but of much coding or vertical organization. Highly encoded scheme that use as compact codes to specify only a single number of control function in each micro instruction are referred to as vertical organization. On the other hand, the minimal encoding scheme in which many resources can be controlled with a single micro instruction is called horizontal organization. The horizontal approach is useful when a higher operating speed is desired and when the machine structure allows parallel use of the resource. The vertical approach result is considerably slower operating speed because more micro instructions are needed to perform the desired control function. Although fewer bits are required for each micro instructions, this does not imply that the total number of bits in the control store is smaller. The significant factor is that less hardware is needed to handle the execution of micro instructions. Horizontal and vertical organization represents the two organizational extremes in microprogrammed control. Many intermediate schemes are also possible in which the degree of encoding is a design parameter. Although we have considered only a subset of all possible control signals, this subset is representative of actual requirement. We have omitted some details that are not essential for understanding the principle of operation. Now let us discuss about microprogram sequencing. Consider the following instruction which adds the source operand to the content of register and places the result in the destination register. Assume that the source operand can be specified in the following addressing modes as register addressing mode, auto increment addressing mode, auto decrement, indexed and indirect addressing mode. A suitable microprogram is presented in the flowchart form for easier understanding. This figure shows the flowchart of the instruction add R source, R destination. Each box in the chart corresponds to a micro instruction that controls the transfer and operation indicated within the box. The micro instruction is located at the address indicated by the octal number above the upper right hand corner of the box. See here, 000, 001, 002, 003 like this, right? Each octal digit represents 3 bits. We use the octal notation in this example as a convenient shorthand notation for binary numbers. Most of the flowchart in the figure is self-explanatory, but some details are being elaborated. We will explain the issues involved first, then examine the flow of the micro instruction in the figure in some detail. The microprogram in figure shows the branches are not always made to a single branch address. This is a direct consequence of combining simple micro routine by sharing common parts. Consider the point labeled alpha in the figure. At this point, it is necessary to choose between the action required by direct and indirect addressing mode. If the indirect mode is specified in the instruction, then the micro instruction in location 170 is performed to fetch the operation from the memory. If the direct mode is specified, this fetch must be bypassed by branching immediately to location 171. The most effective way to bypass micro instruction 170 is to have the preceding branch micro instruction specifying the address 170 and then use an OR gate to change the least significant bit of this address to 1 if the direct addressing mode is involved. This is known as bit ORing technique for modifying branch addressing. An alternate to the bit ORing approach is to use two conditional branch micro instruction at location 123, 143 and 163. Sorry, 166. 123, 143 and 166. Another possibility is to include two next address fields within a branch micro instruction, one for the direct and one for the indirect addressing mode. Both of these alternates are inferior to the bit ORing technique. The microprogram shown in the previous figure requires several branch micro instructions. These micro instructions perform no useful operation in the data path. They are needed only to determine the address of the next micro instruction. Thus, they detract from the operating speed of the microcomputer. The situation can become significantly worse when other micro routines are considered. The increase in branch micro instruction stems partly from limitations to assign successive address to all micro instructions that are generally executed in consecutive order. This problem prompts us to re-evaluate the sequencing technique built around an incrementable microprogram counter. A powerful alternate is to include an address field as a part of every micro instruction to indicate the location of the next micro instruction to be fetched. This means, in effect, that every micro instruction becomes a branch micro instruction in addition to its other functions. The flexibility of this approach comes at the expense of additional bit for the address field. The severity of this penalty can be accessed as follows. In a typical computer, it is possible to design a complete microprogram with fewer than 4 kilo micro instructions employing perhaps 50 to 80 bits per micro instructions. This implies that an address field of 12 bit is required. Therefore, approximately 1/6 of the control store capacity would be devoted to addressing. Even if more extensive microprograms are needed, the address field would be only slightly larger. The most obvious advantage of this approach is that separate branch micro instructions are virtually eliminated. Furthermore, there are few limitations in assigning addresses to micro instructions. These advantages more than offset any negative attributes and make the scheme very attractive. Since each instruction contains the address of the next instruction, there is no need for a counter to keep track of sequential addresses. Hence, the microprogram counter is replaced with a micro instruction address register (MUAR), which is being shown here. Which is this micro instruction address register (MUAR), which is loaded from the next address field in each micro instruction. A new control structure that incorporates this feature and support bit ORing is being shown in the figure. The next addressing bit are fed through the OR gate to the micro address register so that the address can be modified on the basis of the data in the instruction register, external input and conditional code. The decoding circuit generates the starting address of a given microroutine on the basis of opcode in the instruction register. Let us now reconsider the example of micro instruction which we have seen previously, that is the flowchart. Using the microprogram control structure, we need several control signals that are not included in the micro instruction format. Instead of referring to register R0 to R15 explicitly, we use the names RSRC and RDST, which can be decoded into actual control signal with the data in the SRC and DST field of the instruction register. The figure shows a complete format of the micro instruction. This format is an expansion of the format which is being shown previously. Using such micro instruction, we can implement the micro routine. The revised routine has one less micro instruction. The branch micro instruction and location 123 has been combined with the micro instruction immediately preceding it. When micro instruction sequence is controlled by a microprogram counter, the end signal is used to reset the microprogram counter to point the starting address of the micro instruction that fetches the next machine instruction to be executed. In our example, this starting address is 000 to the base 8. However, the micro routine in the figure which is being shown here does not terminate by proceeding the end signal. In this organization, the starting address is not specified by a resetting mechanism triggered by the end signal. Instead, it is specified by explicitly in the F0 field. One drawback of microprogrammed control is that it leads to a slower operating speed because of the time it takes to fetch micro instructions from the control store. Faster operation is achieved if the next micro instruction is prefetched while the current one is being executed. In this way, the execution time can be overlapped with the fetching time. Prefetching micro instruction present some organizational difficulties. Sometimes the status flag and the results of the currently executed micro instruction are needed to determine the address of the next micro instruction. Thus, straightforward prefetching occasionally prefetches a wrong micro instruction. In these cases, the fetch must be repeated with the control address, which requires more complex hardware. However, the disadvantage are minor. The prefetching technique is often used. So that's all with today's content. See you all in the next video lecture. Thank you.